After studying this module, you will be able to learn about vibration of diatomic molecules, population of vibrational energy levels, number of vibrational degrees of freedom, interaction of radiations with vibrating molecules and their selection rules, number of fundamental absorption bands, hot bands and overtone bands, region of vibrational spectrum, evidences in favor of MCO pi bonding. In the rigid rotor model of a diatomic molecules, it is assumed that the covalent bonds are rigid and inflexible, that is, the internuclear distance of atoms connected together by covalent bonds remains constant during rotation of the molecule, but it is not true. In fact, the atoms of molecule do not remain at fixed relative positions, but they vibrate about some mean position. It imparts vibrational energy to the molecule. The vibrational motion of a molecule is confined to very small space and therefore the vibrational energy of molecule is quantized. In other words, a vibrating molecule can acquire only certain discrete values of vibrational energy. When electromagnetic radiations are incident on a vibrating molecule, it absorbs electromagnetic radiation of suitable frequency and it undergoes transition from lower vibrational energy level to higher vibrational energy level, and thus an absorption band is obtained. The spectrum obtained in this way is called vibrational spectrum. It is obtained in the infrared region of the electromagnetic spectrum and therefore it is also called infrared spectrum. When electromagnetic radiations are incident on a vibrating molecule, it absorbs electromagnetic radiation of suitable frequency and it undergoes transition from lower vibrational energy level to higher vibrational energy level, and thus an absorption band is obtained. The spectrum obtained in this way is called vibrational spectrum. It is obtained in the infrared region of the electromagnetic spectrum and therefore it is also called infrared or IR spectrum. By the measurement of IR absorption spectrum, we can derive information about the spacing of allowed vibrational energy levels. On this basis, we can obtain various information about the molecular parameters. It must be noted that when IR radiations are passed through a gaseous sample, both vibrational and rotational energy of gaseous phase molecule change as a result of absorption of radiation quanta. This combination of vibrational and rotational effects results in additional complexity of the spectrum. The spectrum obtained in this way is called rotational vibrational spectrum. It can be avoided by taking the sample in the pure liquid state or in a solution. Each molecule in this case is surrounded closely by neighboring molecules which prevents it from rotating like gaseous molecules. Thus, pure vibrational spectrum is obtained. The covalent bonds of molecules have spring-like nature and they oscillate about some mean position. The covalent molecules may be regarded as harmonic oscillator. The vibrational motion of molecule imparts vibrational energy to the molecule. The vibrational energy of molecule is quantized. The energy difference between two consecutive vibrational energy levels is greater than the thermal energy available at room temperature. Therefore, at room temperature, only ground state vibrational energy level, that is V is equals to 0, is populated and the excited energy levels are almost unoccupied. The number of vibrational degrees of freedom for nonlinear molecule is 3n minus 6 and for linear molecule is 3n minus 5. The mode of vibration which leads to oscillation in the vertical component of the dipole vector can interact with the electromagnetic radiation and give rise to vibrational spectrum. Such molecule absorbs IR radiation and undergoes transition from V is equals to 0 to V is equals to 1, producing fundamental band which is sharp and generally strong. The wave number of the fundamental band increases with increase in the force constant of the bond. The free CO molecule exhibits fundamental band at 2143 centimeter inverse due to stretching mode of vibration. The position of fundamental band shifts to lower wave number for coordinated CO molecule due to MCO pi bonding, and it further decreases with increase in the extent of back pi bonding. The positive charge on metal increases the CO stretching frequency because it discourages back MCO pi bonding. The negative charge on metal facilitates the back MCO pi bonding and hence it decreases the CO stretching frequency. Let us see the vibration of a diatomic molecule. Two atoms A and B of a diatomic molecule may be regarded as two balls of masses Ma and Mb, and the covalent bond connecting these atoms may be regarded as weightless spring holding such balls together. In the diagram which is shown here, we have three cases. In the first case, the molecule AB is in the compressed position. In the second figure, the molecule is at the mean position where the bond length between the atom A and atom B is the equilibrium bond length, and in the third figure, the molecule AB is in the stretch position. Because of the spring-like nature, the covalent bonds vibrate constantly and obeys Hooke's law for harmonic oscillator. It states that the restoring force acting on a system undergoing simple harmonic motion is directly proportional to its displacement from the mean position. Such molecules are called classical harmonic oscillators. The frequency of vibration of vibrating diatomic molecule is given by nu is equals to 1 by 2 under root k upon mu, where k is the force constant of the bond. It is the measure of toughness or stiffness or the strength of the bond. Greater the value of k, stronger will be the bond. It is defined as the force required to displace the bond from the mean position by a unit distance. Its unit is dynes per centimeter or newtons per meter. Where mu is the reduced mass of the molecule, which is equal to the mass of atom A into mass of atom B divided by the sum of the masses of atom A and atom B. The vibrational energy of diatomic vibrating molecule is given by E is equals to h upon 2 pi under root k by mu into V plus 1 by 2, where V is the vibrational quantum number whose value changes from 0, 1, 2, 3 and so on. It is obvious that the vibrational energy of molecule is quantized and it can acquire only certain discrete values as shown in the figure. You can see from this figure there are various vibrational levels having different vibrational energies, and you can see that the vibrational energy of molecule increases with increase in the value of V. The energy difference between the two consecutive vibrational energy levels is constant and is equal to h upon 2 pi into under root of k upon mu. The molecule has a certain vibrational energy even in the lowest vibrational energy level, that is the V is equals to 0. The vibrational energy of a molecule in the lowest vibrational energy level is called 0 point energy and is equal to 1 by 2 h upon 2 pi into under root k upon mu. The vibrational energy of a molecule with increase in the value of force constant and decrease with increase in reduced mass of the molecule. On combining equation 1 and equation 2, we get E vibrational as h nu into V plus 1 by 2. Now we will see the population of vibrational energy levels. The energy difference between the ground state vibrational energy level, that is V is equals to 0, and the first excited vibrational energy level, that is V is equals to 1, is h upon 2 pi into under root of k upon mu, and it is much larger than the thermal energy available at room temperature. Therefore, most of the molecules are present in the ground state vibrational energy level, that is V is equals to 0, and the excited vibrational energy levels, that is V is equals to 1, 2, 3 and so on, are almost unpopulated at room temperature. At higher temperatures, the excited vibrational energy levels are populated to more or less extent. Now let us see what are the number of vibrational degrees of freedom. A linear diatomic molecule has only one vibrational degree of freedom, and it is the stretching and the compression of bond, and leads to the to and fro motion of the atoms connected by it. For a polyatomic molecule having n atoms, number of vibration degrees of freedom, that is the number of fundamental modes of vibration for nonlinear molecule, is 3n minus 6 and 3n minus 5 for linear molecule. In this table, the number of fundamental modes of vibration are calculated for water and carbon dioxide. As you know that the water is a bent molecule, on applying 3n minus 6 rule, you can see that there are 3 fundamental modes of vibration, whereas for carbon dioxide there are 4 fundamental modes of vibration. You can see from this diagram that the 3 fundamental modes of vibration for water is shown. The first is symmetric stretching, in which both the bonds are stretching simultaneously. The second is antisymmetric stretching, in which one bond is stretching and other bond is compressing. And the third is the bending mode of vibration, in which the angle between HOH changes during bending. When you see the second diagram, it shows the fundamental vibration modes for the carbon dioxide molecule. The first one shows the symmetric stretching, in which both the bonds are stretching simultaneously. In the second figure, you can see there is an antisymmetric stretch, in which the one bond is compressing and the other one is stretching. The third one is the bending vibration mode. The bending mode of vibration of CO2 molecule is doubly degenerate. The stretching modes of vibration involve rhythmic back and forth movement of atoms linked together by covalent bond, and during this process the distance between the atom decreases and increases periodically. The bending vibrations occur in molecules having more than two atoms which are not directly connected by a covalent bond, and it involves a change in the angles between bonds with a common atom. Now we see the interaction of radiation with vibrating molecule. There are two selection rules for the interaction of vibrating molecules with the electromagnetic radiations and the transition of molecules from one vibrational energy level to the another vibrational energy level. The fundamental mode of vibration of a molecule which leads to oscillation or fluctuation in the vertical component of dipole moment of molecule periodically is infrared active, that is, can interact with IR radiation, and the molecule can undergo transition from one vibration energy level to another vibration energy level. For example, the symmetric stretching mode of vibration of CO2 molecule is IR inactive because it does not lead to the fluctuation in vertical component of the dipole moment of the molecule. On the other hand, the antisymmetric and bending modes of CO2 molecule are IR active. It has been shown in the figure. You can see from the first figure the IR inactive symmetric stretching mode of vibration for CO2 molecule. Since there is no change in the dipole moment, all these modes are IR inactive, whereas in the antisymmetric stretching for CO2 molecule, there is a change in the vertical component of dipole moment periodically, which gives rise to the IR active mode of vibration. Only those transitions between the vibration energy levels are allowed which lead to the change in the vibrational quantum number by unity, that is, delta V is equals to plus minus 1. Since most of the molecules are present in the ground state vibration energy level, the only possible transition between vibration energy level is from V is equals to 0 to V is equals to 1, and the absorption band arising in this way is called fundamental absorption band. The energy required for this transition can be given by the energy of electromagnetic radiation absorbed during the transition from V is equals to 0 to V is equals to 1 as energy of V is equals to 1 level minus the energy of V is equals to 0 level, as shown in this workout, which leads to the value of fundamental wave number or frequency as 1 by 2 C into under root of K by mu, where nu bar fundamental is the position of fundamental band in centimeter inverse. The position of fundamental bands of some diatomic molecules and their force constant are given in this table. Number of fundamental absorption bands. The heteronuclear diatomic molecules such as HF, HCl, HBr, HI, CO, NO, etc. are IR active and they have only one fundamental mode of vibration, and it is stretching mode of vibration. Such molecules exhibit only one fundamental absorption band in the IR spectrum. On the other hand, the polyatomic molecule have more than one fundamental mode of vibration, that is, more than one pattern of vibrational energy levels. Each fundamental mode of vibration produces one fundamental absorption band. Therefore, polyatomic molecules exhibit more than one fundamental band in the IR spectrum. For example, H2O exhibits 3 fundamental bands in the IR spectrum at 1595 centimeter inverse, which is due to the symmetric bending mode of vibration, 3652 centimeter inverse, which is due to symmetric stretching mode of vibration, 3756 centimeter inverse due to antisymmetric stretching mode of vibration. Now let us see what are hot bands and overtone bands. At the room temperature, only ground state vibrational energy level is populated by molecules and the excited vibrational energy levels are almost unoccupied. But at higher temperatures such as 200 degrees centigrade, the first excited vibrational energy level, that is V is equals to 1, is also populated appreciably, and the transition from V is equals to 1 to V is equals to 2 will give rise to a weak band in addition to V is equals to 0 to V is equals to 1 transition. The absorption band arising due to the transition from V is equals to 1 to V is equals to 2 is called hot band. Its intensity increases with increase in temperature due to the increase in the population of V is equals to 1 vibrational energy level. The vibrating molecule do not behave perfectly like a harmonic oscillator. It means the restoring force is not exactly directly proportional to the displacement from the mean position. Such molecules are called enharmonic oscillators. As a result of this enharmonic motion, there is relaxation in the selection rule, that is, delta V is equals to plus minus 1, and some weak absorption bands are also observed due to transition involving delta V is equals to plus minus 2 or delta V is equals to plus minus 3. These are called overtone bands. The origin of various absorption bands has been represented in the diagram. You can see from this diagram the transition 1 shows the transition from V is equals to 0 to V is equals to 1, and the name of this absorption band is fundamental absorption band. The transition 2, which is from V is equals to 0 to V is equals to 2, is the first overtone band. The transition from V is equals to 0 to V is equals to 3 is the second overtone band, and the transition from V is equals to 1 to V is equals to 2 is the hot band. The intensity of the absorption bands decreases in the sequence. Fundamental absorption band is much greater than the first overtone band, which is greater than the second overtone band. Now let us see the region of vibrational spectrum. The vibration spectrum is generally scanned in the wave number range 650 cm inverse to 4000 cm inverse, which falls in the infrared region of the electromagnetic spectrum, and therefore it is called IR spectrum. The IR spectrum is generally divided into two regions. One, the fingerprint region. The absorption bands in the range 650 cm inverse to 1250 cm inverse are more numerous and associated with a number of rotational and vibrational energy changes in the molecule, and therefore less valuable for the identification of the functional groups. This region is called fingerprint region, and it is quite useful in determining whether two samples are identical or not. Two identical samples have identical pattern of absorption bands in this region, but different compounds have different patterns of absorption bands in this region. Second, group frequency region. The absorptions in the region 1250 cm inverse to 4000 cm inverse involve the change in the vibrational state of various bonds and are generally characteristic of the types of bonds or functional group present on the molecule. There are relatively a few peaks in this region, and their position is only slightly changed from one molecule to another molecule. This region is called group frequency region, and it is very useful in the identification of the functional group present in the molecule. Now let us see the evidences in favor of MCO pi bonding. From the vibrational spectra of metal carbonyls, it is possible to infer directly and semi-quantitatively the existence and extent of MC multiple bonding, that is MCO pi bonding in metal carbonyls. This is more easily done by studying CO stretching frequencies rather than MC stretching frequencies. This is due to the fact that the former give rise to strong and sharp bands which are well separated from the other vibrational modes of the molecule. On the other hand, the MC stretching frequencies are in the similar region with other types of vibration. For example, MCO bending modes of vibration, and therefore the assignment are not easy to make. The prediction of MC bond orders from the behavior of CO vibration is based on assumption that the valency of carbon is constant, so that a given increase in MC bond order must cause an equal decrease in the CO bond order, which in turn will cause a decrease in the CO vibrational frequency. Free CO molecule exhibits an absorption band at 2143 cm inverse. due to its stretching mode of vibration. The MCO pi bonding places the electron density of metal diatomic orbital of the central metal to the vacant antibonding pi star molecular orbital of CO molecule. As a result, the CO bond order of coordinated CO molecule decreases. It decreases the force constant of CO bond, which leads to the shift in the position of CO absorption band to shorter wave number region. You can see from the table, greater the extent of MCO pi bonding, greater will be the electron density transferred from metal diatomic orbital to the central metal to the vacant antibonding pi star molecular orbital of CO molecule. Lower will be the CO bond order, lower will be the force constant of CO bond, lower will be the CO stretching frequency, and lower will be the wave number of CO absorption band. This fact has been verified experimentally by IR spectra. The positive charge on metal in a metal carbonyl discourages MCO pi bonding, and therefore it increases CO stretching frequency in comparison to the metal carbonyl with neutral metal. On the other hand, the negative charge on the metal in a metal carbonyl facilitate MCO pi bonding, and therefore it decreases CO stretching frequency. These facts are supported by the following IR spectral data. The covalent bonds of molecules behave like spring and they vibrate about a mean position. The vibration motion of molecule is confined to a small space, and hence the vibration energy of vibrating molecule is quantized. The energy difference between the ground state vibrational energy level and the first excited vibrational energy level is much greater than the thermal energy available at room temperature. The mode of vibration which leads to fluctuation in vertical component of the dipole vector of molecule can interact with the electromagnetic radiation. Such vibrating molecule undergoes transition to higher vibrational energy level involving delta V is equals to +1 by absorbing EMR of suitable frequency. The vibrational spectrum is obtained in the IR region of the electromagnetic spectrum, and it is also called IR spectrum. Number of vibrational degrees of freedom is 3n-6 for nonlinear molecule, while 3n-5 for linear molecule. The absorption band arising due to transition from V is equals to 0 to V is equals to 1 is called fundamental band. The transition from V is equals to 0 to V is equals to 2 is called first overtone. The transition from V is equals to 0 to V is equals to 3 is called second overtone, and at higher temperatures excited vibration energy level, that is the V is equals to 1, is populated appreciably, and the transition from V is equals to 1 to V is equals to 2 produces a weak absorption band known as hot band. The intensity of hot band increases with increase in temperature. The wave number of fundamental absorption band increases with increase in the force constant, that is the bond order of the bond. Free CO molecule exhibits vibrational absorption band at 2143 cm inverse. Coordinated CO molecule exhibit vibrational absorption band at lower wave numbers due to MCO pi bonding, which decreases the CO bond order. The positive charge on the metal, this favors MCO pi bonding, and hence it increases CO vibrational frequency, while the negative charge on metal reverses this effect.